Okay, so today I'm going to be doing the review sheet for the matrix unit, going through each of the problems on here to help you prepare for the test. I try to pick questions that were very similar to the ones on the test. So if you can do the ones on the review sheet today, you should be good for the test. Okay. So starting off with number one, we got the Leslie model. Okay, so this is a typical Leslie model question that you might run into. I will be giving you a chart that looks like this, or you might have to create one, but for the most part, just having a chart's good enough. And you'll be given the chart with the initial population in it. Okay? So as long as you can remember that the population distribution for any cycle is equal to the initial matrix, your initial row matrix, times your Leslie matrix, raised to the k power, representing the number of cycles, okay, you'll be able to figure out these answers for any time period. Okay? So let's do A. It says, how many newborns will there be after 5 cycles? Well, in order to do this problem, you need to have a P sub 0 matrix and a Leslie matrix. Okay? So your P sub 0 matrix is equivalent to, well, just the numbers in this chart. Okay? It's just your initial amount of animals or initial amount of population that you have for each age group. So in this case, 22, 22, 18, 20, 7, and 2. Okay, so that's your initial population. Let's talk about how to create the Leslie matrix, the other matrix you need to do this problem. Okay? It's going to be a square matrix, and it's going to be using the information from the birth rates and the survival rates. Okay? So the first column is going to always be your birth rates. Okay, so these numbers right here. So putting those down in your first columns, 0, 0.5, 1.1, 0.9, and 0.4, and 0. Okay, because we have 6 different age groups, 1, 2, 3, 4, 5, 6, we're going to have 6 different birth rates in our Leslie matrix. And then remember, for the survival rates, they're going to go in your remaining columns, but one at a time down a diagonal. So I'm going to start off with the 0.6, and then zeros everywhere else. Oops, 1, 2, 3, 4, 5, 6. All right, then I'm going to do the 0.8 in the next column. It's going to go 0.8, 0, 0, 0, 0. Then I'm going to do the 0.9, so that's going to be 2 zeros, the 0.9, 0, 0, 0. Okay. Then I'm going to do the 0.8, so that's going to be 0, 0, 0, 0.8, 0, 0. And then you end with the second to last one. That'll make your square matrix. So I'm going to end with the 0.6, 0, 0, 0, 0, 0.6, 0. There's my Leslie matrix. Okay. So we have our P sub 0, we have our Leslie matrix, and we can do it to any amount of cycles. Okay. So in order to solve this problem, all you have to do is do this initial row matrix, P sub 0, multiply it by the Leslie matrix we just came up with, and since we're doing 5 cycles, we're going to raise it to the 5th power. Okay. So when you do that in your calculator, which I can't really show on these notes, but when you do it in the calculator, I get the following numbers. Now again, you drop the decimal. You round everything down in these problems because we don't have fractional parts variables. I'm getting 61, 32, 22, 20, 17, and 4. So there's your population distribution after 5 cycles. This is saying that I have 61 newborns, 32 4 to 8 month olds, 22 to 8 to 12 month olds, 20 12 to 16 month olds, or year olds, whatever these cycles are in terms of month. And then 16 or 17, 16 to 20 month olds, and 4 20 to 24 month olds. That's the population distribution. Okay. I could let's see. Now B, I'm asking you to find the population distribution and total population after 3 cycles. Okay. So again, for B, it's going to be the same exact equation: P sub 0 times my Leslie matrix. But now, since I'm doing it in 3 cycles, you raise it to the 3rd power. In this case, I'm getting 47, everything rounded down, 47, 28, 25, 10, 13, and 8. That is your population distribution after 3 cycles. Now, if I want the total population, you just add all these numbers up, and that ends up equaling 131. What are these things? Small mammals. So the next type of example that we have is a Markov chain. A Markov chain is another application with matrices, and that's talking all about probability. Okay, probability. Now, remember with Markov chains, it's the same exact formula as Leslie matrix. It just looks a little different. Okay? If I wanted to know what state, what probability I'm going to have after k amount of transitions, it's equivalent to whatever our initial row state matrix is. Whatever our initial state row matrix D sub 0 is, times something called our transition matrix. That will always be a square matrix. That's raised to the k power. This is the k represents the number of transitions. Okay. So let's read this type of problem. It says a hospital categorizes patients as well, good, critical, and deceased. Data shows that the hospital's patients move from one category to another according to the probability shown in the transition matrix. And this is showing what happens daily. Okay. So here's initially where I'm at. So I'm well, good, critical, or deceased. And it tells the probability of going from one state to the next state. Okay? So for instance, the probability of going from good to critical is only a 20% chance. Okay, so that's what the transition matrix tells us. Now, if I need to write an initial state matrix, which is my D sub 0, it depends on what the problem's giving you. In this case, it's a patient who enters the hospital in critical condition. Okay? Well, since it's a row matrix, it's going to have the same amount of entries as a square matrix. So 1, 2, 3, 4 possible states that this person can be in, either well, good, critical, or deceased. Well, since he's 100% critical, then that means that he is 0% well. He is 0% good. He is 100% or 1 critical, and he's 0% deceased. This is the initial state that this person is in when he comes into the hospital. Now, if I take this critical person and I want to know that the number of transitions daily after 1 full week, I want to know what this patient's condition would be after 1 week. You would take your D sub 0 here, okay, and you would again multiply it by your transition matrix, which is this matrix here. But after 1 week, that is 7 transitions, so you raise it to the 7th power. And here, I probably round to 2 or 3 decimal places, but what I'm getting is a row matrix, 0.564, 0.062, 0.09, and 0.284. So that's the breakup of the probabilities of what state he's in. What I'm saying is there's a 56.4% chance that he's well. There's a 6.2% chance that he is good. There's a 9% chance that he's critical. And there is a 28.4% chance that he is deceased. Okay, so know how to interpret those values. All right, moving on to game theory. So with game theory, you're going to have something called a payoff matrix. Okay, a payoff matrix. And it's going to be a square matrix, and it's going to be talking about the strategies that you could have in the rows versus the columns. What you're going to be able to know how to do, is create this payoff matrix and then interpret those values. Okay, so what we're doing in A and B here is already given the payoff matrix, interpreting how to solve this problem. Okay, so it says each of the following matrices represent a payoff matrix for a game. Find the max and min and the min and max. So we're going to go through all the steps that we need to know how to do game theory. If the game is strictly determined, find the saddle point of the game. If it is strictly determined, talk about the best strategies. Now, these are general cases. We don't know what game or situation is going on here, so we'll call these strategies A, B, and C, A, B, and C. We'll talk about some game where each person has strategies A, B, and C. Okay. So the first step in A is to figure out your row minimums. Again, those are your worst case scenarios for each strategy. So in this case, that would be for row 1 or row A, -3, -2 for the second row, and -4 for the third row. Okay. Now what you want to do is then find the maximum value or the maximum of your minimum values, the maximum of those three numbers, which in this case is -2. So what I'm saying is the worst case scenario for playing strategy B is -2. That would be the strategy that you would lose the least amount of money. Now vice versa, you want to do a column maximum. Okay? Because that's going to be the worst case scenario for the person in the columns. In this case, your column maximums in column A is 2, in column B is 3, and in column C is -2. Okay? So now then what you want to do is find the minimum of those maximum values, called the min and max, which in this case is -2. That, of the worst case scenarios, that is the one that he would lose the least. In this case, for the person in the columns, he'd be gaining 2 pennies. That's what the negative means. All right. So since we have a min-max and a max-min being the same value, that's called a saddle point. So my saddle point in this case is equal to -2. That tells us that we have a strictly determined game. And because of that, we can determine the best strategies. In this case, for the person in the rows, the best strategy is the one that gave him that -2. His would be to do strategy B. For the person in the columns, the one that gave him -2 was column C, so his best strategy is to always play C. And that's it. That's how you do this problem. That's the work. Okay? Let's try the second one. Okay? It's a little bit easier because it's a 2x2. So again, we'll call this strategy AB, this strategy AB. So let's start off by finding the row min. Okay? Your row minimum values here are 0 and -2. And of those minimum values, your maximum, the maximum of those, is equivalent to 0. Now, vice versa, we want to do the row, or the column, I apologize, the column maximum. Okay. In this case, the column maximums would be 0 and 3. And of those, the min and max, or the worst case scenario in the columns, is 0. Now look, your max and min and your min and max, those are 0. Okay? So that means your saddle point is 0. It means that it is strictly determined. We're good, which means we can assume a best strategy to always play. For the person in the columns, or in the rows here, his best option that gave him the max and min of 0 would either do strategy A. The one for columns would be the one that gave him 0, for him to also play strategy A. That would work out best for both. Now another cool note to see here is that if you notice, the saddle points are both 0. That means that the payout is in favor of no one. This would be considered a fair game. Something kind of cool to keep in mind. Okay, now we're going to talk about some matrix basics. Okay, just to kind of refresh yourselves. This is the same stuff that was on the quiz. Just kind of refresh yourself on what to do so you don't get these wrong on the test. Okay, it's helpful to know how to do them all by hand as well on the calculator. Okay, save some time. Now, state the size of each matrix. Identify the indicated element. Okay, so the size of this matrix is a 2x2, 2 rows by 2 columns. Now, remember what this notation means. This says A12. This means the element in row 2, which is this row, with column 1. That's this number here. That's equal to 4. It's just the indicated element in the matrix. This is a 2 by 3 matrix. 2 rows by 3 columns. A23, that's row 2 with column 3. That's equal to 9. So know how to do those. 6 and 7. simple problems. Know how to add them together. They have to be the same side, and you just add the corresponding parts. 12 and 0, negative 5 and 3, 10 and negative 2, 4 and 7. Okay, I ended up getting 12, negative 2, 8, and 11. Now, if you look at this one right here, this is a 3 by 1 and a 2 by 2. They don't match up. They're not the same size, so we can't add them. Does not exist. For number 8, multiply each matrix by the given scalar factor. Okay, again, this is gimme points. This is just distributing the value through to every single number in the matrix. Okay, so everything multiplied by negative 1 on number 8. So I'm just getting simply 0, negative 4, negative 6, negative 3, 2, and 7. Same thing for number 9. Just multiply 2 by everything. You're distributing that value through. I'm getting negative 8, 2, 4, negative 18, 12, and 6. All right, so evaluate each determinant. So it's really helpful to know how to do these by hand. So talking about number 10, if I'm finding the determinant, remember you just multiply the diagonals. So 3 times 4 is 12, and you're going to subtract them. So 12 minus 2 times negative 1 is negative 2. So I'm going to do 12 subtract negative 2, which is equal to positive 14. Same thing for number 11. I'm going to do 2 times 7, which is 14, and subtract 3 times 1, which is equivalent to 11. Now, with a 3 by 3 matrix, the only way to solve that determinant is to do it in the calculator. Okay? Remember that you're going to go to your matrix menu, so it's really second x negative 1. You're going to scroll over to math, and it's the first option, number 1, which is DET of something. So you're just going to take the DET of this matrix, and I ended up getting, in this problem, 393. All right, number 13 and 14 are gimme points. It says determine whether each matrix product is defined. If so, state the dimensions of the product. A times B. Remember, in order to do these problems, the inner dimensions have to be the same. So in this case, since they're both 2, then yes, we can find the product, and the outer dimensions are the product's dimension. So AB's dimensions are equivalent to a 3 by 4. Here, these are the same size matrices in number 14, but the inner dimensions are not the same, so we can't find the product. This one does not exist. All right, finding the product. Finding the product. Right, undefined for the expressions that can't be multiplied. I feel very confident y'all can do this in the calculator. Let's refresh ourselves on how to do this by hand. All right, this is a 2 by 2 matrix multiplied by a 2 by 3 matrix. All right, so because they are the same inner dimensions, I know that I can find a product. Their product's going to be a 2 by 3. So I'm going to draw. I'm going to do it right about right here. 2 rows with 3 columns. That's kind of what it looks like. 1, 2, 3, 1, 2, 3. Okay. And actually, for the sake of space, I'm just going to go ahead and do this one in the calculator. I'll do number 16 by hand. Okay, but if you do this in the calculator and multiply them, you're going to get 4, 12, 28, 19, negative 42, and 79. But okay, just for sake of space, I don't want to write all the work for that. But for number 16, let's refresh how to do that one by hand. Okay. Again, okay, so this is a 2 by 3 matrix and a 3 by 2 matrix. Because of the same inner dimensions, I can find the product, and their dimensions is going to be a 2 by 2. All right, 2 rows, 2 columns. This one's a lot easier to show work in this video. Okay. All right, so for the top left one here, if I'm doing this entry right here, I'm looking at the rows with this matrix with the columns of this matrix. So if I'm looking at this first number here, that's the first row in the first matrix with the first column in the second matrix. So this row with this column. Just make sure when you're multiplying the corresponding parts. The first with the first, so 1 times 7 plus 2 times 9 plus 3 times 11. Okay? That's the first with the first, second with the second, third with the third. Okay? That ends up being 58. Same thing for the next one. Okay? This entry right here, this is the second row with the first column. So that's 4 times 7 plus 5 times 9 plus 6 times 11, which ends up being 139. All right, here in this top right one, we're in the first row again, so the first row with the second column. So this entry right here. So that is going to be now 1 times 8 plus 2 times 10 plus 3 times 12, which ends up giving us a value of 64. And then lastly, we're looking at the last row with the last column. So that's this last row here in this matrix with the last column in this matrix. 4 times 8 plus 5 times 10 plus 6 times 12, which then would equal 154. Okay? So make sure you know how to do those by hand. All that you see here for number 16, that's the work I'm looking for. Okay, that's what I expect to see. On this last one here, we got a 3 by 1 multiplied by a 2 by 3. Inner dimensions are not the same. This product does not exist. Transposing or give me points. All that means is to take your rows and make them your columns. So this was a, let's see here. So what I'm going to do, so I'm going to take this first row and make it my first column. So 7, -3, -5. My second row becomes my second column, and my third row becomes my third column. Give me points. Here, this was a 2 by 3 matrix, so now it's going to be a 3 by 2 matrix. My first row becomes my first column. My second row becomes my second column. And that's your answer. That's what it means to transpose. Done. Okay. Decide whether the given matrices are inverses of each other. Okay? I'll do 20 with you by hand, the other one in the calculator. Look, all you have to do with these problems are multiply. Matrix A multiplied by matrix B. Okay? Now, if they equal the identity matrix, which is 1, 0, 0, 1 for a 2 by 2, or 1, 0, 0, 0, 1, 0, 0, 0, 1 for a 3 by 3 matrix. If it equals either one of those, then they are inverses of each other. So let's show number 20 by hand. Okay? So all we have to do is multiply. So we're doing this with this with this. Okay? So that's a 2 by 2 matrix multiplied by a 2 by 2 matrix. Inner dimension is the same. Our product is going to be a 2 by 2. Alright, show the work. So we got a 4, so first row, first column is 4 times 1/2 plus 1 times -1, and that ends up giving us 1. So we're on the right track. This bottom left one here, so that's going to be 4 times 1/2 plus 2 times -1, which ends up being 0. So it's looking good, looking good. Then we're going to do the top right one here. So that's row 1, column 2. So that is 4 times -1/4 plus 1 times 1, which is, again, 0. Yay! So this last one has to be a 1 in order for them to be inverses of each other. So that's going to be 4 times -1/4 plus 2 times 1. Awesome. And that ends up being 1. So those are inverses of each other. Check. We have proved that, and we're good. That's your work for that. Now, let's do 21 in the calculator. So that's just going to do matrix A times matrix B. When I end up multiplying those, the product that I get is negative 0.2, 1.36, negative 2.067, and 0.667. Obviously not inverses of each other because it is not the identity matrix. So no, those are not inverses. All right, let's refresh finding the inverse of a matrix by hand. Okay, an inverse of a matrix by hand. Remember, we can only do it for a 2 by 2 by hand. In order to do that, it's 1 over whatever the determinant is. That's the part you'll always forget. Multiplied by, and remember, you're going to switch the first diagonal. Switch whatever those two elements are, and change the sign of the other two diagonals. And that's the formula. Then distribute the 1 over the determinant value through, and you have your final answer. So let's do 22. The first step is to find the determinant, which again is 3 times 2 is 6, minus 5 times 1, which is 1. Our determinant is 1. The formula states to do 1 over the determinant, okay, 1 over the determinant, which in this case we just found was 1. And we're going to multiply it through. We're going to switch the first diagonal. So 3 and 2 switch to 2 and 3. And we're going to switch the signs of the second diagonal. So negative 5 and negative 1. Okay. Now, since the determinant is just 1 over 1, if I were to distribute that value through, it doesn't change anything. So my final answer is 2, negative 1, negative 5, and 3. For 23, okay, let's do that. So if I take the determinant equals 10 times 3 is 30, subtract 5 times 6 is 30. In this case, it equals 0. Remember what happens. If our determinant is ever equal to 0, think about how the formula is going to work. That's 1 over 0, which doesn't work. If you ever have a determinant of 0, we have no inverse. It does not exist. And lastly, to do 24, you can't do that by hand. You have to do that in the calculator, and you have to raise that to the negative first power. Okay, that's really the only way to do it in the calculator. And that's just, that's the button. It's 4 buttons down. You use it all the time. You might have to change it to a fraction. Okay, it might end up being ugly decimal. So remember, you can just go to math and choose the first option, which is fractions, and just hit enter. And the answer I'm getting is negative 1/3, negative 2 over 3, 2/9, negative 7/18, 10 over 9, 1/6, 1/12, negative 1/6. Okay, so that's the inverse. And lastly, the last thing I want to do with you is talk about how to decode a message. This was the last application of the 4 applications we did with matrices. It wants us to decode the message 82, 83, 23, 0, all the way to 133 here. Okay. It was encoded, though, using the matrix 4, 3, negative 1, 5. So if I want to decode it, what I'm saying is that this square matrix was used to encode it. So to undo it, I need to do the inverse. Inverse will undo it. So what I'm going to do is take that 4, 3, negative 1, 5, and take the inverse of that, and multiply it by the 2 by whatever matrix with these numbers in it. Okay? And just remember how you do it. It's by column. So the first number goes here, the second number here, and you're going to keep putting those numbers in the correct order that they're written in the list. Now this ends with an even amount of numbers, but remember, if for some reason, say it ended with a 5 here, you need to make sure, well, in the most cases, that'll always work out, so don't worry about that. Okay? All right, so we got our setup. If you just multiply that out, how you know you're doing it right is if the matrix comes out with numbers between 1 and 27. Then the matrix can be decoded. And this is what I'm getting when I multiply these two. All numbers between 1 and 27. Now, taking the numbers out in the same order, okay, we get 7, 18, 5, 1, 20. 27, 10, 15, 2, and 27. Now, using our decoder where the numbers associate with the letters, we get G, R, E, A, or A, T, space for 27, J, O, B, and space again. And our message in this case that we decoded was great job. Great job is the message, and great job for watching this video, great job for doing your work. Hopefully this all makes sense, and hopefully this video helps. So good luck on your tests, and